Hello, my name is Connor Wallace. I'm a PhD student in the University of Texas at San Antonio's Electrical Engineering Department, and I will be presenting a paper entitled GeoDA, a Geometric Framework for Black Box Adversarial Attacks by Ramati et al., which was published in the proceedings of the 2020 CVPR conference. In model evasion attacks, an adversary is concerned with perturbing an input sample as little as possible to evade detection, while still forcing the model to misclassify the sample. To give some intuition to the approach, consider the decision boundary here between the correct class, represented by the green area, and the incorrect class, represented by the red area. With respect to these local decision boundaries, the adversary looks to add just enough perturbation to push the sample across the boundary and force a misclassification. Geometrically, the most efficient way to do this is to move the sample in the direction of the normal vector between the original sample and the nearest decision boundary. To do this, the adversary needs an estimate of the magnitude of the normal vector. In other words, the adversary must estimate the location of the decision boundary before computing the minimum distance required to cross it. There are several different types of attacks that have been developed recently that can be grouped into three main categories: white box attacks, gray box attacks, and black box attacks. White box attacks assume that the adversary has nearly unlimited knowledge of the targeted model. This includes model architecture, model parameters, training data, and so on. Traditionally, white box models are by far the most successful attacks as they have access to as much information as possible. However, white box attacks are not very feasible for real-world risk encounters. Somewhere in the middle are gray box attacks that make more constrained assumptions but still require prior information about the targeted model. Black box attacks, however, assume very little about the targeted model but tend to present a much more difficult problem. One of the more approachable black box problems is in the score-based setting, where confidence scores for each label are provided by the model API. This, however, allows the algorithm to directly estimate the gradients and come to a solution more efficiently. More difficult than this, but more realistic, is the setting of decision-based inquiries when only the hard labels are provided. This typically requires less efficient estimation of the perturbation direction from sampled model queries. Within this setting, there are top K models, where the K most likely hard labels are provided from the model API. This allows for both better estimation of decision boundaries as well as designing targeted attacks. However, one of the most difficult black box tasks are top 1 models where only the hard label of the maximum probability is provided. This is the most realistic scenario for adversarially perturbing closed model APIs, which naturally make it an ideal research topic. Within the space of decision-based black box attacks, one of the most prominent attacks is the boundary attack. This attack starts off with an image with a large adversarial perturbation and performs a random walk, trying to stay close to the decision boundary while minimizing the distance to the original image. While being highly intuitive, this approach does suffer from being inefficient in the number of queries it takes to converge to the optimal perturbation. The hop-skip-jump attack builds off of the boundary attack by introducing a gradient estimate instead of a random walk. By estimating a gradient, it allows the adversary to converge to the optimal perturbation in a much more efficient way than the boundary attack. Because of this efficiency, it is acceptable to consider this attack the state-of-the-art baseline in black box decision-based settings. The authors previously introduced an algorithm they called QFool, which adapts the boundary point search problem to a heuristic search based on the L2 norm, where the normal vector between the current point and the decision boundary is estimated and used as the minimum perturbation. This estimation is done by sampling perturbations from a multivariate normal distribution and deriving the optimal perturbation vector from the mean of the observed adversarial distribution. Building off of the successful work on QFool, the authors generalized the approach to L2 and L-infinity norms to create a new algorithm they called GeoDA, as well as provide the solution for the L1 norm to create an additional algorithm called sparse GeoDA. To achieve this, the authors framed the problem as a non-targeted evasion attack, solving the following optimization problem. The general form optimization problem is to minimize the distance function between the original sample x and the adversarial sample x perturbed by v, such that the classification of x is not the same as x plus v. Borrowing the ideas of QFool, the authors reframe the optimization problem by solving for the difference between the perturbed sample and the nearest decision boundary point xb and linearizing this equation based on the generalized LP heuristic metrics. Here we present the general form GeoDA solution. By setting the distance function to the general LP norm of the perturbation vector v, we can rewrite the optimization problem. By assuming the hyperplane that passes through the nearest boundary point xb also passes through the origin, we can treat the distribution of perturbed queries as a hyperplane truncated multivariate normal distribution. With this distribution in mind, the authors come to the general form solution for the perturbation vector v at iteration t. The general adversarial update at iteration t is the solved vector v multiplied by a scaling factor r, which is generally assumed to be non-negative, but with certain conditions can be optimized via a line search algorithm along the vector v. Here the authors present the specific solutions to the L1, L2, and L infinity norms. For the L infinity norm, the general form solution simply reduces to the signum function of the current normal vector estimate. As said previously, the scaling factor is an arbitrary non-negative parameter that can be optimized with a line search. The L2 norm, however, presents a clean solution that reduces to the current normal vector estimate. The scaling factor also has a closed form solution in the L2 norm of the original sample and the current adversarial estimate. The authors present a slightly modified approach for solving the L1 norm case. They introduce a constrained optimization problem where the perturbed sample is constrained to a lower and upper bound. This allows the algorithm to identify and concentrate on which pixel coordinates have the highest impact to movements towards the decision boundary without having to modify much of the rest of the original image. Here the authors provide several experiments to prove the validity of their approach. To experiment, the authors have chosen to use a ResNet 50 classifier, which has been pre-trained on ImageNet. The experiments generally follow the process of adversarially perturbing an input X and feeding the adversarial example to the model and retrieving the max label. The main experiments performed test three capacities: efficiency of convergence, the effectiveness of the attack, and a direct comparison between sparse GeoDA and a state-of-the-art sparse white box attack as a baseline. Here are the metrics the authors used to validate the results on the ImageNet validation set. First, the authors used the median L2 and L infinity distances between the original and adversarial examples to compare efficiency among algorithms. Second, the fooling rate is used to showcase the effectiveness in forcing misclassification as a percentage of total queried examples. Finally, the percentage of affected pixel coordinates is used to determine the efficiency of sparse GeoDA. The authors now present qualitative and quantitative results validating the efficiency and effectiveness of the proposed adversarial approach. These example images showcase the different effects of the L2, L infinity, and L1 versions of GeoDA. It can be seen that the L2 norm results in a more diverse and severe set of pixel coordinate perturbations. The L infinity norm, however, also affects a set of pixel coordinates, but with a much softer perturbation, which is potentially extremely valuable in evasion settings. Finally, the L1 norm, as designed, only affects a sparse set of pixels with a much higher severity. It should be noted that the perturbations to the right of the original images are scaled up approximately 10 times for better visibility. Here the efficiency of the proposed algorithm is shown. For both L2 and L infinity median distances, GeoDA is far superior to boundary attacks. GeoDA also achieves a bump in performance over QFool and hop-skip-jump attacks. However, QFool converges more efficiently, yet at a higher perturbation cost. Additionally, GeoDA manages to achieve superior perturbation distances while converging quicker than two of the other black box attacks, as well as the Carlinian-Wagner white box attack. Finally, it should be noted that the L infinity distance of GeoDA is comparable to the L2 distance achieved by DeepFool and Carlinian-Wagner, two state-of-the-art white box attacks. These results show the convergence of GeoDA versus boundary and hop-skip-jump attacks. Figure A shows the number of queries versus the converged distance for the L2 version of GeoDA. Figure B, however, shows the number of queries versus the required number of iterations to converge to the optimal perturbation for the L2 version of GeoDA. The plots show that GeoDA and hop-skip-jump are considerably more efficient than boundary attacks. While GeoDA and hop-skip-jump converge to a similar perturbation distance, GeoDA remains more efficient after larger numbers of queries. Figure C, on the other hand, shows the fooling rate versus the sparsity of the perturbed pixel coordinates for sparse GeoDA for 3 levels of queries. This shows that no matter how many queries requested, sparse GeoDA converges to roughly the same fooling rate after perturbing approximately 6% of the pixel coordinates. Finally, the authors compared the performance of sparse GeoDA against the sparse fool, a state-of-the-art white box sparsity attack. While sparse GeoDA doesn't achieve the same level of success as sparse fool, it manages to come close given a significantly more constrained set of information. Finally, the authors have presented a novel adversarial attack for the top 1 decision-based black box setting. They then provided solutions for the general form LP norm, as well as specific mathematical and algorithmic solutions for L2 and L infinity norms, as well as the L1 norm for sparsity, resulting in 2 novel algorithms, GeoDA and sparse GeoDA respectively. They finally presented extensive experimentation showing the effectiveness of the algorithms compared to both black box and white box approaches, thus achieving the new state-of-the-art and top 1 decision-based black box settings. I hope that you found this talk informative for adversarial evasion attacks and that this might serve as a basis for future research in the space of top 1 decision-based black box attacks. Thank you.